The screened and degritted sewage is further conveyed towards the biological treatment step. Can we remove some part of the organic upfront to minimize energy requirements in the bioreactors? In this lecture we will discuss the principles and design of the primary settlers or primary clarifiers. After passing the screens and grit chamber, the sewage merely consists of organic pollutants. About 50% of the pollution load is present as suspended solids, of which a large part is settlable in clarification tank as indicated in this slide. Suspended solids of organic nature are non-discrete particles and follow the flocculant settling pattern as discussed in a previous lecture. They coalesce with other particles during settling, leading to increased particle density and thus increased settling velocity. At the upper part of the clarifier, the flocculant settling process occurs, whereas at the lower part, the hindered settling is dominating. The occurring mechanisms of particle enlargement are flocculation and coagulation. In the primary clarifier, the settleable organic solids are removed via the bottom, whereas the floating organic matter is skimmed from the top part of the tank. A primary clarifier may remove up to 50–70% of the suspended solids and about 25–40% of the BOD. Primary clarifiers are constructed in circular tanks as well as in rectangular tanks. In screens and grit chambers, the hydraulic flow velocity is very high, but for the primary settler, the flow velocity needs to be reduced by at least a factor of 10. Therefore, the inlet works and flow distribution of the incoming flow into the clarifier are important design aspects. At the inlet, an energy dissipation of the incoming flow is required to avoid turbulence that might affect the settling process. A circular clarifier is equipped with a bridge that moves slowly clockwise with the help of a motor which is mounted at the extreme of the bridge. In the slide you see a cross-section of the clarifier with the bridge serving two purposes. At the down part of the bridge a bottom scraper is mounted that gently moves the settled solids to the central core of the clarifier. From here the settled sludge is pumped to another treatment device, for instance a sludge thickener. At the top part, just under the bridge, a surface scraper is mounted that gently skims the surface from floating organic matter. Also the collected floating matter is collected at the central point and conveyed to a subsequent treatment step. The basic settling principles in circular or rectangular tanks are the same, but construction-wise, there are some differences. In rectangular tanks, the inflow is distributed at the lateral side of the clarifier and leaves the tank at the opposite extreme. The bottom scrapers are mounted on a chain which is driven by gears as shown in the slide. This construction, however, can be vulnerable and regular maintenance is required, for which a tank needs to be emptied. Directly under the bridge, a surface scraper is mounted to skim the floating organic material from the surface. Are all sewage treatment plants equipped with a primary settler? No. The so-called oxidation ditches and carousels are directly fed with non-settled sewage. As a result, all organic material, including the settleable organic solids, need to be stabilized in the aeration tank. And as a consequence, the required volume of aeration tanks needs to be bigger and more energy is required. In fact, oxidation ditches and carousels have less process units than shown in the slide schematized the activated sludge process, which for instance is used in the city of Delft. For primary settling, no mathematical formulas apply. However, increasing density and increasing size will lead to improved settling performance, similarly to discrete settling. In addition, increased particles concentration will lead to enhanced flocculation and thus higher efficiency, provided the particles have a high ability to flocculate. Increase in liquid turbulence will immediately decrease the efficiency of flocculant settling, as illustrated in the graph. Ideally, the flow regime is non-turbulent, which will lead to the settling of the particles according to the settling path of particle B. Turbulence may cause drastic deviations from this flow regime as indicated by the settling path A. Now, how can we reduce Reynolds number in order to reach a more laminar flow regime? Most ideally, the influent is distributed equally over the entire inlet area, resulting in a more or less laminar flow without any areas of hydraulic short-circuiting. Inadequate flow distribution may bypass large areas of the clarifier, resulting on the one hand in dead spaces and on the other hand in areas which have much higher flow velocities than foreseen. Also, circular tanks may develop unstable flow regimes as a result of inadequate flow distribution or improper energy dissipation of the incoming flow. In a primary clarifier, we try to reach a stable flow regime, characterized by a high resistance to flow disturbances. Temperature, and particularly the temperature differences within the tank, may largely impact the sedimentation performance of the clarifier. From the discrete settling principles, we learned that with increasing temperature the liquid viscosity will drop, leading to an increase in Reynolds number and thus a higher turbulence. With Reynolds numbers less than 2000, this will result in a drop of the drag coefficient and thus increase in the terminal particle velocity. Under laminar flow conditions, this will lead to enhanced settling. However, temperature difference may create areas of lower density next to areas with a higher density. And the resulting effect is a short-circuiting of the liquid, reducing the actual settling volume, leading to a worse performance. Density differences may be caused by incoming sunshine. In addition to temperature-induced density differences causing active flow volume reduction, also strong winds may impact the flow regime. How can we design a tank that is resistant to flow disturbances? For creating hydraulically stable flows, we have to take the Froude number into consideration. The Froude number, in fact, defines the resistance to flow disturbances and should be higher than 10 to the power minus 5. The Froude number can be expressed in the dimensional measures of either a rectangular tank or a circular tank. Based on the required Froude number, rectangular tanks should be narrow and long, and circular tanks should have a large diameter. But note here that large diameter tanks are more susceptible for weather influences. In contrast to discrete settling, the tank depth is crucial in flocculant settling. A higher depth enlarges the chances for flocculation, as is illustrated in the slide. But note that it will be more difficult to guarantee laminar flows in more deep tanks. The depth of a tank is determined by the allowable scoring velocity or the maximum allowable horizontal velocity. The lower the depth, the higher the scoring velocity. In discrete settling, we discussed that a relatively high scoring velocity of 0.3 meter per second is applicable to separate sand from organic solids. For primary sludge itself, the maximum scoring velocity is about a factor 10 lower, so 0.03 meter per second. For sludge from the bioreactor, the so-called activated sludge, this value drops to 0.02 meter per second. The allowable scoring velocity is dependent on a number of factors, such as the diameter of the particles, specific gravity of the particles, material constant, and the Darcy-Weisbach friction factor. While leaving the exit of the clarifier tank, the water flow should keep its non-turbulent flow pattern, which is determined by the weir overflow loading. However, flow acceleration towards the weir cannot be prevented, as shown in this slide. For primary clarifiers, a weir loading of 10 to 15 cubic meter per meter is allowed. A too high loading will cause light material to leave the tank. In circular clarifiers, the sludge is collected in the bottom core of the tank by using a rotating bridge, under which bottom scrapers are mounted. In circular tanks, the maximum speed of the outer edge of the bridge is about 0.06 to 0.07 meter per second. Note that in rectangular tanks, a maximum bridge speed of 0.03 meter per second is applied. The collected sludge is either removed continuously or semi-continuously, but retention times inside the primary clarifier should be less than 1 day. This to prevent sludge digestion in the tank and the production of bad odor. The solids and BOD removal efficiency is a function of the applied hydraulic retention time in the tank. Considering the fluctuating incoming flows, removal efficiency will accordingly fluctuate when duration of the peaks exceed the design HRTs. The shown constants A and B are empirically assessed and will differ per clarifier and per location. The current slide lists the most important design guidelines of primary clarifiers. Maximum flow surface loading rate should be designed as 1.5 to 2.5 cubic meter per square meter per hour. However, whenever the average flow rate equals the maximum flow, even higher values up to 4 cubic meter per square meter per hour can be applied. The average hydraulic resonance time, or HRT, is about 5 hours. The minimum HRT during peak flows should not be less than 1 to 1.5 hours. The depth of the tank is between 1.5 and 2.5 meter, and the bottom slope, to facilitate sludge collection, is about 1 to 10 to 1 to 12. Round tanks must have a diameter between 20 and 60 meters, otherwise arm is too long, and with an optimum size of about 30 to 40 meter. If needed, the number of tanks must be increased. Rectangular tanks have a maximum length of 90 meters and an optimum length of about 30 to 50 meters. The applied width is generally 5 to 6 meters, but could be increased up to 12 meters, demanding more attention to bridge construction, of course. The width-length ratio is about 1 to 5 to 1 to 6, whereas the depth-length ratio is about 1 to 20. The pre-screened, degritted and clarified sewage is still full of soluble pollutants. Physicochemical removal of these pollutants will be too expensive. In the next lectures, therefore, we will discuss how to engineer natural conversion processes in compact bioreactors.